apart from the homework, we've got some things to talk about here today. Um, let's get started with some schematics and how you can use a circuit drawing to kind of analyze the circuit. So, this is baby's first circuit. And the simplest circuit you can draw has just one battery, a wire, and another wire connecting it to a single resistor. Now, I'm going to specify that this battery is a 12-volt battery. That's a car battery. And that this resistor has 24 ohms of resistance. And so the very first thing you can do is you trace the circuit and make sure it is indeed a complete circuit. And then we can establish that some current will flow out of the battery. And of course, that same current will flow around this corner, go through the resistor, flow around this corner, flow around this corner, and return to the battery. So the current has nowhere to go but the one circuit. There's no splitting up of the currents or different currents. So we can find the one current for this circuit using Ohm's law. And Ohm's law says that V equals I times R. In this case, it's the voltage for the whole circuit, the resistance for the whole circuit, and the current of the whole circuit. We can monkey this around so that it says I equals V over R. That's just algebra, or using the magic triangle. And we can put the numbers in. We have a 12-volt resistor. I'll drop the units later. And a 24 ohm. Oh, did I say resistor? I meant battery. I have a 12-volt battery and a 24 ohm resistor. And this is clearly going to be exactly 1/2 of an amp. So we can also apply Ohm's law just to this resistor. Now that we know that 1/2 of an amp is flowing through this resistor, we can figure out how much energy, how much voltage this resistor is dissipating. And this resistor is dissipating a voltage that's equal to the current through it times its resistance. And the current through it is 0.5 amps, and the resistance is 24 ohms. So we get back 12 volts. So this resistor is dissipating 12 volts. That's a number associated with it. It has a resistance of 24 ohms, and it has a current flowing through it of 0.5 amps. This circuit has a voltage of 12 volts, a total resistance of 24 ohms, and this current is 0.5 amps. Now you might say, hey, this is a little redundant, Harmon. You use the voltage and the resistance to get the current. You put the current back in here, of course you're going to get this voltage back. That's how math works. True, but there is something a little more interesting we can do with a circuit. So let's draw the next most interesting circuit. And in this case, I'm going to have two resistors. I decide to place one up here and one over here, and then we still need one wire to bring this all home to the battery. Oops, I overshot a little bit. Still a 12-volt battery, but now we have two of these 24 ohm resistors. Okay. Well, we trace the circuit, make sure it is a circuit. Yes, we have a continuous path for charge to go all the way around. And we realize that there's going to be some current that comes out of the battery. I'll call it current BAT. There's going to be some current that goes through this resistor. There's going to be some current that goes through this resistor. And there's going to be some current that comes back home to the battery. Okay, well, let's do the whole circuit thing now. For the whole circuit, the voltage for the whole circuit is equal to the current flowing out of the battery times the total resistance. I'm adding some subscripts because of the words I said after I said these things. I want to look at the whole circuit as one big piece. Well, the whole circuit voltage is the only voltage that's here. It's 12 volts. The current coming out of the battery is currently unknown to us. And the total resistance, well, we go through a 24 and then we go through a 24. So the total amount of resistance is going to be 48 ohms. Or I could have done this thing up here and flipped these over to get 12 divided by 48. But either way, the current that comes out of the battery is going to be 0.25 amps. So So we now know that the current that comes out of the battery is 0.25 amps. That means that the current that goes through this resistor is 0.25 amps, since the current has nowhere to go but is forced to go through this resistor. And the current going through this resistor is 0.25 amps. Well, I guess the current going back into the battery must be 0.25 amps. So don't add up the total current. Oh, yeah, that's a total of 1 amp. No, it's the same 0.25, right? And I'll show you a picture that demonstrates this later. Um, but now we can talk about each of the resistors individually. The voltage across resistor number 1 is going to be the current through resistor number 1 times the resistance of resistance number 1. And so the voltage dissipated by resistor number 1 is going to be 0.25 times 24. And 0.25 times 24 is 6 volts. Oh, hey, this guy only dissipates 6 volts. He only consumes 6 joules for every coulomb of charge out of the 12 that came out of the battery. And that's because the voltage dropped by number 2. Dropped is another word that's used for voltage. Dissipated, dropped, consumed. Because it's energy. It's energy that's being used. Maybe to do something, maybe to do nothing. Sounds like some of us at times, using energy to do nothing. All right, same situation, same math here, same result here. 6 volts is going to be dissipated. Now we understand that the total consumption of voltage is what adds up as you go around the circuit. So let's draw a bigger version of this, and we can draw our little charge dudes going around the circuit and having a good old time. So what did the circuit look like? Sorry, I've got too many papers over here. Okay, centered. Here we go. All right, so the circuit looked like a battery, a resistor, another resistor, and a wire. Okay, so what we had here is we had a bunch of charge dudes come out of the battery, and I'm going to represent 0.25 amps as 2 charge dudes. When they came out of the battery, they had 12 volts worth of energy. That's a very significant lightning bolt on top of their helmets. Now those two go through here, and while they're in here, they have to drop off 6 volts of their energy. So when they come out the other side, we still have 2 of them, but their lightning bolts are now significantly smaller. Okay, these had 2 jaggy jaggies. These have 1 jaggy jaggy. And now they go through this resistor. They have to do whatever this resistor asks of them. In fact, I think of this as an obstacle course, like in the military. You come running out of the starting line, you've got to go through the tires, and then you've got to climb the cargo rope, and then you get to go home. Well, they're going to lose 6 more volts here. So when they come out over here, there's still going to be 2 charge guys, but they are going to be dead dog tired. They're going to have no lightning bolts. They go back with 0 voltage. And this is the same too as they ground this corner and they head home to the battery. So we have the same current everywhere, but we have a different state of charge. These guys came out with 12 volts worth of energy. They lost 6, so they have 6 volts worth of energy here. They lost 6 more, and so they have 0 volts. They always go home with 0 volts. No matter how much energy they're given back in this battery here, they always find a way to lose all of it on their trip around the circuit. Now, someone once asked me, hey, Harmon, how is it possible that the electrons and charges that don't have consciousness can tell before they even come out of the battery, before they even go through the first obstacle, what the next couple of obstacles are going to be like and how much energy they have to save for each one? And I want you to know that this charge dudes analogy falls apart because it requires consciousness and decision making on the part of the charge dudes. No, what really happens is there's a massive flow of charge out of a battery, and it goes through the resistors, and each charge loses a random amount of energy, but they average out to 6 volts, and the whole thing works itself out so that the total amount of energy added back to the charges by the battery is dissipated by the things they have to go through, and the amount of charge that comes out comes into balance, and so everything works out in large statistical numbers. But little charge dudes is a great way to think about that. So the battery adds energy to the charges, the resistors subtract energy from the charges, and then the overall resistance governs how many charges decide they're going to come out and do the obstacle course. The easier the obstacle course, the more charges will come out. And all of that flows from Ohm's law. V equals I times R. Applied once to the whole circuit and once to each resistor. Okay, that's our little lesson for today.